So let's talk about ice albedo effect. The ice albedo effect is a positive feedback in which, particularly in regions where there's ice and snow, if it warms up a little bit, then some of that ice or snow melts. And if enough of it melts to expose either dark ground or, more significantly, dark open water, then that diminishing of the ice cover causes more dark surface to show. The albedo goes down. That causes more sunlight to be absorbed. That causes more heating, and that exacerbates the effect because it causes more ice or snow to melt. And so we get this cyclic positive feedback, the ice albedo feedback. And the ice albedo feedback is a really important feedback mechanism in the climate system. And it's the reason, as I've stated several times, why we expect and are seeing that the Arctic regions warm a lot faster than the rest of the globe, and why we're seeing particularly dramatic climate change in the Arctic, particularly the Arctic, not so much the Antarctic, because the Arctic ice, most of it is floating sea ice. It overlies dark water, and as we reduce the coverage of sea ice, we increase the absorption of solar energy because we've reduced the reflectivity, and that further exacerbates the heating effect. So ice albedo effect is a very important positive feedback effect. There's another effect. There's a cloud albedo effect. And the cloud albedo effect is opposite. It's a negative feedback. What happens? Well, suppose there's a little bit of an increase in Earth's temperature. One thing that does is cause more evaporation. If there's more evaporation, more clouds form. Clouds at their tops have a high reflectivity. They reflect sunlight, and they therefore reduce the amount of sunlight getting into the climate system, and that causes Earth's temperature to go down. That's a negative feedback. Now, you might say, well, hey, we can stop global warming with these negative feedbacks, but if you look at feedback effects, especially those that occur sort of in proportion to the effect that's originally driving them, you can show mathematically that the best a negative feedback effect can do is to reduce the initial warming, but it can never turn it into a cooling. It can never reverse the initial thing that started out. The most it could do, if it were an infinitely strong feedback effect, would be to halt that warming altogether, but no feedback is like that. So the best you can do with negative feedback is simply to reduce the initial effect, but you can't eliminate it or reverse it. So that's cloud albedo feedback. There's another important feedback called water vapor feedback, also related to evaporation. Water vapor feedback is a positive feedback. If the Earth warms, there is more water vapor in the atmosphere, but water vapor is a greenhouse gas. And so there's a bigger greenhouse effect. And water vapor is a significant greenhouse gas. We believe today that global warming caused by carbon dioxide emissions is enhanced by about 50% by the water vapor feedback effect. Because water vapor goes in and out of the atmosphere so instantaneously, we don't regard water vapor as a greenhouse gas that we put there. We regard it as something that instantaneously adjusts to the current climate conditions. But there is this water vapor feedback, and that probably enhances any warming from other factors by about 50%. Some feedbacks may even involve human behavior. Suppose it gets real warm, for example. Lots of more people go out and buy air conditioners. They plug them into the wall. If they live in a region where their electricity comes from fossil fuels, they then produce more carbon dioxide, which causes more warming. Now, that's probably a trivial one in the grand scheme of things, but it illustrates that we human beings can have a role in these feedback effects and therefore altering the climate system. I want to emphasize that feedbacks work in either direction. The ice albedo feedback, if the Earth began to cool, that would cause more ice to form, that would reflect more sun, and that would cause it to cool further. That's still a positive feedback. It doesn't matter whether the initial effect was in one direction or the other. If the effect is enhanced, it's still a positive feedback. Well, I've talked a lot about computer models, some of what they contain, some of their imperfections, some of the things we're doing to make them better. How do we know that these computer models are any good? Well, we have considerable confidence actually in the models. Climate scientists are doing a lot of things to test their models. First of all, and I showed you one example of this in the previous lecture, if you start a climate model in the distant past, or 100 years ago, a couple hundred years ago, at the start of the industrial era, some of them started much further in the past, and you run them to the present, you can make them reproduce present conditions, at least if you put in everything we know about what's driving the climate system. So climate models started in the past can successfully reproduce the present-day climate. They can also reproduce some other pretty obvious things. For example, if you had a climate model that included the tilt of the Earth's axis and the seasons and so on, it better be able to reproduce seasonal temperature variations, or you want to throw that model out. Well, models do reproduce things like seasonal temperature variations easily. Climate models reproduce also a number of other details of Earth's climate system that you might not think about. For example, I mentioned that climate models have many boxes representing the different layers of the atmosphere. Well, we aren't just concerned about surface temperature. If a climate model reproduces the climate accurately, it ought to reproduce the temperature at all levels in the atmosphere. And if you run a whole bunch of different climate models and compare their results for the vertical structure of the atmosphere, averaged over the planet, to what we actually observe for that vertical structure, you find remarkable agreement between the climate models and the observed vertical structure of the atmosphere. So there's a subtle thing that you might not think about that the climate models very successfully reproduce. If you look at patterns of precipitation, for example, how does precipitation depend on latitude? So you average over longitude, because longitude is a less significant variable in terms of climate than, again, latitude, pole to equator to pole. You find, and precipitation is a more difficult and subtle thing to deal with, you find nevertheless that the computer models do a very good job of reproducing the latitudinal distribution of precipitation. They all show a big rise in precipitation at the equatorial regions. There's a drop in the sub-equatorial regions, like where the Sahara Desert is, and then a rise into the temperate zones, and then a fall off as you go toward the poles. There's another example, something rather subtle you might not have thought of, that those climate models, many, many different climate models by many different groups, are nevertheless successfully reproducing. That's about current climate and how the models reproduce various aspects of current climate. If you project into the future, one of the reassuring things is that the models from different climate modeling groups working independently, having written different models with different subgrid parameterizations and different other features, do a pretty good job of consistently reproducing the future climate, or agreeing on what the future climate should be. A common experiment that climate modelers do is to subject their model to a 1% per year increase in the amount of carbon dioxide. And if you look at a dozen or so different climate models, again, from around the world, and how they do at that rise in temperature with increasing CO2, most of them cluster very close to the same average value, which comes out somewhere between 1.5 and 2 degrees Celsius rise at the end of a period of about 80 years. A couple of the models are a little further outlying. They all show an increase. None of them show a decrease. And the increase they show is pretty much consistent. So models are verified in a great many ways. What we'd really like to do with our models is say, okay, let's do an experiment with the real climate system and see if our model can reproduce the outcome of that experiment. Well, that, as I've argued many times, we can't do. However, Earth does provide us with some natural climate experiments. And I want to give you one example of one. And that experiment is the eruption of Mount Pinatubo in June of 1991. The Pinatubo volcano put enough dust into the atmosphere to qualify it as the second biggest eruption of the 20th century. And it put enough dust in the atmosphere, high into the atmosphere, to produce a measurable global cooling. And when the Mount Pinatubo eruption went off, climate scientists said, let's run our model with the amount of dust that this eruption has put into the atmosphere, and let's see what our model predicts for the climate of the next few years. And they ran their model, and they then waited a few years until we had global temperature records for the years following the Mount Pinatubo eruption, and they then compared them. And I want to show you a graph of that result. So Mount Pinatubo eruption is really a natural climate experiment, and the graph I'm showing has a dark curve that represents the actual observed global temperatures in the years following the Pinatubo eruption. There are two dashed curves which represent the results of model runs. They're slightly different because they make slightly different assumptions about the amount and properties of the dust the volcano ejected into the atmosphere, but they're pretty similar. And you can see very clearly a good qualitative and largely quantitative agreement. As soon as the volcano erupted, the global temperature fell. It fell quite significantly by about 0.5 degree Celsius, not quite 0.5 degree Celsius, and then it took a number of years to recover. And by the way, if you look at Earth's global temperature in the early 1990s, or look at records of what were the warmest years on record, the years 1992, 1993, 1994 tend not to be as high up in those lists as you think, and that's because of the Mount Pinatubo eruption, causing a global cooling that was measurable and reproducible with climate models. So let me summarize. We have complicated simple to complicated models, the more complicated ones being large computer programs that run and try to simulate the climate, try to project the climate of the future. They include things like feedback effects. They include subgrid parameterization effects for very small scale phenomena. They are verified by a number of verification schemes, including particularly this natural Mount Pinatubo experiment. So we have some confidence that they give us a reasonable projection of what future climate ought to look like under conditions we specify.